Welcome to Study Loop.
For this problem on the topic of waves and sound, we are told that a theodolite is a device used to measure distance by measuring the time required for an ultrasonic pulse to reach a target, reflect, and then return to the device. So when the device is properly calibrated, it uses the speed of sound for the appropriate ambient air temperature to determine the distance between the theodolite and the target. So if we suppose that the device is calibrated so that it gives a correct value for distance at a temperature of 291 Kelvin, we want to know the value for the same distance when used at a temperature of 298 Kelvin, and we want to know if the incorrect value is smaller or greater than the correct value. We'll assume that air behaves as an ideal gas. So traveling at a speed v for the round trip between the theodolite and the target, the sound wave travels a distance 2x, which is equal to v times t, where t is the round-trip travel time and x is the one-way distance for target. Now, we'll have to apply that the equation that v is equal to the square root of gamma k t over m for an ideal gas, where gamma is the ratio of specific heats, k is the Boltzmann's constant, t is the temperature in Kelvin of the gas, and m is a mass of a molecule of air. Now, the first thing we can do is find the percentage error in the incorrect value when measured by the theodolite. The percentage error is equal to the incorrect distance minus the correct distance divided by the correct distance multiplied by 100. That'll give us the percentage error. And we can write this as the incorrect distance over the correct distance minus 1 multiplied by 100%. And we'll call this equation 1. So that's the formula to calculate percentage error. Now, if we use the expression from above, 2x is equal to vt, we write the one-way correct and incorrect distances measured by the theodolite as follows. So the correct distance is equal to a half v, the speed of sound at 291 Kelvin, times the time at 291 Kelvin. So that's the time it takes for the signal to reach the theodolite. And we also have that the incorrect distance is equal to a half times the speed of sound at 291, but the time it takes for the sound wave to return at 298 Kelvin. Now, if we use these expressions, we can see that the ratio of the incorrect to the correct distance needed in equation 1 is as follows. So x incorrect over x correct is equal to the time at 298 Kelvin divided by the time at 291 Kelvin. We'll call this expression number 2. Now, if the theodolite were calibrated correctly for the measurement at 298 Kelvin, then both the measurements would yield the same one-way correct distance, and we would have that the correct distance would be a half v at 291 times t at 291, and this would also be a half v at 298 multiplied by the time at 298 Kelvin. So these both will give the same distance, x correct or xc. Now, since the two correct values of the one distance must be the same, it implies, therefore, that a half times v 291 times t 291 must equal to the equation on the right, which is a half v 298 times t 298. And if we take ratios, we get this to be T 298 over T at 291 must equal the ratio of speeds. Speeds of sound, V 291 over the speed of sound at 298 Kelvin. Now, if we assume that air behaves as an ideal gas, and we know that the speed of sound is equal to the square root of gamma kT over m, we can take, so we'll call this expression, this ratio, we'll call it equation 3, and we apply the expression for V for an ideal gas. In equation 3, we get that T at a temperature of 298 over the temperature at 291, which we said was V 291 over V 298. We can then use the expression for a sound wave in an ideal gas, which is the square root of gamma times K, which is constant, times the temperature, 291 Kelvin, divided by the mass of air, divided by the square root. And at 298, the only thing that will change is the temperature, which now becomes 298 Kelvin. The mass, gamma, and K all stay constant. So this simplifies to the square root of the ratio of temperatures. So essentially, it's the square root of 291 Kelvin over 298 Kelvin. We'll call this equation number 4. Now, if we substitute 4 into 2, we get that the ratio of the incorrect to the correct distance we saw is T 298 divided by T 291, and this is simply the square root of T 291 over 298 Kelvin, the temperature at 298. We'll label this expression 5. So if we take this expression 5 and we substitute it into our initial expression for the percentage error, we get the percentage error is equal to the ratio x incorrect over x correct, the incorrect distance over the correct distance, minus 1 times 100%. And from above, this becomes the square root of the ratio of temperatures at 291 Kelvin over the temperature at 298 Kelvin, minus 1 times 100%. We know this obviously to be the square root. The temperature at 291 Kelvin is obviously 291 Kelvin, and this is divided by 298 Kelvin. This square root minus 1 times 100% will give us the percentage error. And the percentage error in the theodolite, if we calculate this, is minus 1.2%. And the negative answer in this percentage error tells us that the incorrect value of the distance is smaller than the correct value.